Okay. Hello, everyone. Today, I'm going to present a paper titled Parameterized Knowledge Transfer for Personalized Federated Learning, and it is published in NIPS this year. Here is outline. Firstly, I'm going to give you the motivations of personalized federated learning. Next is the algorithm proposed in this paper called knowledge distillation personalized federated learning. Finally, I will conclude this paper with the performance evaluation part. First of all, let's move to the motivation part. We all know that federated learning has emerged as an efficient paradigm to collaboratively train a shared machine learning model among multiple clients without directly accessing their private data. But there still remains a crucial challenge that significantly degrades the learning performance. That is the data heterogeneity. For example, for IID data settings, we can find a global model which will satisfy all local clients. But for these non-IID data settings, the global model cannot always be generalized well over each client. And in this case, we can employ the personalized federated learning framework, where for each client, we will have one specific local model instead of the global one. So that's the motivation of the personalized federated learning. For personalized federated learning, it can personalize the global model for each client. And the most existing approaches of personalized federated learning are based on a regularization term or meta-learning ideas. The regularization-based methods means that we can add one regularization term for the local loss function, and then it will control the distance between the local model and our global model. Meta-learning methods means that we can train a global model which can be quickly adapted to local clients. But all these methods, they only consider the homogeneous model settings, which is not practical because the neural network models should be adapted to heterogeneous capacities in computation, communication, and storage space, etc. So recently, there appears one technique called knowledge distillation. It can deal with this heterogeneous model issue. From this knowledge distillation, the knowledge can be transferred from a neural network to another one by exchanging soft predictions instead of using the whole model parameters. But there are still some problems of this knowledge distillation solutions because for these solutions, they ignore the personalized requirements. They only maintain one global model. So they don't consider some personalized issues. Therefore, in this paper, the goal is to learn a personalized federated learning framework, which can accommodate the heterogeneous model structures and achieve the personalized knowledge transfer among different clients. That's the goal of this paper. Next, let's move to the algorithm part. The algorithm proposed in this paper is a knowledge distillation personalized federated learning. Firstly, let's look at the problem formulation. We aim to collaboratively train personalized models for a set of clients applying different model structures in federated learning. For example, we have the number of n clients, and for each client, we have it has its own data set. Xi is the input data and Yi is the label. So for the conventional federated learning framework, the goal is to learn a global model parameter W that minimizes the total empirical loss. However, this formulation has some limitations. The first one is that it requires all clients to have a unified model structure, which cannot deal with the heterogeneous model structure issue. The second one is this formulation minimizes the total empirical loss, which is not suitable for heterogeneous data. So in this paper, they propose a personalized loss function for each client, as shown in this equation. For this loss function, the first term is a conventional loss function. It is a cross entropy between the model predictions and the label. And the second term is the KL divergence function. It can transfer the personalized knowledge from a teacher to a student. And for this KL divergence function, S is collaborative knowledge, and I will introduce this term later. And the CMN is a knowledge coefficient. It can estimate the contribution from client M to client N. And for this KL divergence function, it will be trained based on the public dataset. And for this conventional loss function, it will be trained based on the private dataset. So according to this KL divergence function, the first term can be seen as the teacher, and this one can be seen as the student. Therefore, if we optimize the local model parameter Wn, the knowledge can be transferred from the teacher to the student. That's the physical meaning of this KL divergence function. Next, let's look at the details of this collaborative knowledge and this knowledge coefficient. The collaborative knowledge can refer to the soft predictions or model parameters. And in this paper, they use the soft prediction as the collaborative knowledge, which can be denoted as this equation. And in this equation, ZCN is the output of the last fully connected layer of the class C, and T is the temperature hyperparameter of the softmax function. So S is the output of the softmax layer, which should be a probability vector. Therefore, the goal of this KL divergence function is to let the soft prediction of the target client N approach to the soft prediction of the teacher. The knowledge of the teacher is the weighted sum collaborative knowledge of all clients. Accordingly, if we optimize this KL divergence function, it can transfer the knowledge from teacher to the student. Next, let's see this knowledge coefficient. It can estimate the contribution of the client M to client N, and it can be obtained from this knowledge coefficient matrix. For example, if our target client is client N, we will choose the column N to calculate the teacher's collaborative knowledge. So that's the function of this knowledge coefficient. And in this paper, this parameter can be seen as an optimization variable. Thus, the objective function of the federated learning problem can be formulated as this equation. And in this equation, we have two types of the optimization variables. The first one is the local model W, and the other one is this knowledge coefficient matrix. And here, for this objective function, we add this regularization term. It can ensure the generalization ability of the whole learning system. For example, and in this regularization term, the rho is a hyperparameter which can trade off the personalization and the generalization. And one here is the identity matrix. Let me explain this regularization term and this hyperparameter rho. For example, if we set rho equal to 0, which means we don't have this regularization term. And in this situation, the optimal solution of the knowledge coefficient matrix should be that the CNN equals to 1, the other CMN equals to 0. And in this way, the KL divergence loss function should be 0, and it will be the optimal one. And in this situation, there is no collaboration. We only have this local loss function, and it only has the personalization ability. But if we set rho equals to 1, in this case, the regularization term will let each coefficient approach to 1 out of n. So each client will learn the knowledge from all other clients equally, because for all CMN, it should be equals to 1 out of n. And in this way, it can ensure the strong generalization ability. Therefore, the rho is a hyperparameter which can trade off the personalization and the generalization in this learning system. Are there any questions here? Okay, so let's move to the next part. After having the objective function, the authors propose a KTP-FL algorithm to solve it. And the main idea of this KTP-FL algorithm is that the local model parameters W and this knowledge coefficient matrix are updated alternatively. So in each run, we fix either W or C by turns and optimize the unfixed one following an alternating way until a convergence point is reached. Next, let's see the details of the solution. Firstly, we update the client model parameters W locally. It's a two-stage framework. The first stage is the local training. By following the conventional federated learning problem, we train this local parameter Wn on each client's private dataset by using the stochastic gradient descent method. And the second stage is the distillation stage, where the knowledge can be transferred from the personalized soft prediction. And this step will be executed based on the public dataset. Again, here we use this KL divergence function as the loss function and use the gradient descent methods to optimize the local parameter. Next, let's move to the updating of this coefficient matrix C. And for this coefficient matrix, it will be updated in the server. Again, we following a gradient descent minor. We just fix the local parameters of all local models, which means we fix the W term and use the gradient descent method to optimize this C term. And here we still use this KL divergence function and add the regular. Summarize the training procedure of their. The first step is that we can execute the local training based on the local data set. And the second one is after having the local model, we can output the local soft prediction based on the public data. The third step is that we can send this local soft prediction to the server. After receiving the local soft predictions, the server will calculate each client's teacher's personalized soft prediction based on user's local soft prediction and this coefficient matrix. The next step is that each client will download the personalized soft prediction to perform local model parameters. The last server will update the knowledge coefficient matrix, where we fix the user's local model and update this coefficient. So that's the algorithm part of this KTP-FL algorithm. Next, let's move to the performance evaluation part. And here we firstly we look at these experimental settings. The authors consider 3 different tasks, which means they consider 3 different training data sets. eMNIST, Fashion MNIST, and CFAR10. And they choose MNIST as the public dataset for eMNIST and Fashion MNIST. And they choose CFAR 100 as the public dataset of CFAR 10. Because these papers, they consider the model heterogeneous issue. So they consider 4 different image classification models here: LeNet, AlexNet, ResiNet, and ShuffleNet. And they assume there are 20 clients. So each 5 clients will have 1 type of the model. For the learning settings, they execute 20 local training epochs and 1 distillation step in each communication round. They also compare their methods with several baselines. For non-personalized distillation-based methods, they consider the FedMD and FedDF. FedMD means they utilize the aggregated softmax scores to guide the local model, which means there is no personalization here. There is no personalization in this method. FedDF means they only maintain 1 global model in the server. So again, this method doesn't consider the personalization issue. And they also compare their method with 1 personalized distillation-based methods. We call it pFedDF. pFedDF is a modified version of the FedDF, where we fine-tune the global model of the FedDF with client's own dataset, which means we fine-tuning this global model to personalize it. The authors also compare their proposed KT-PFL algorithm with some simplified version of their methods called similarity PFL and the top K PFL. Similarity PFL means we calculate the coefficient matrix based on the cosine similarity. If the cosine similarity between 2 softmax predictions is larger, the coefficient of these 2 clients will be large too. And the top K PFL method is that we choose the top K client with large cosine similarity to participate in the teacher's soft prediction calculation. And this paper, they consider the data heterogeneous issue where each client contains all labels, while the number of samples for each class is different from that of a different client. And these 3 figures show their simulation results. From these 3 figures, we can easily find that the proposed KT-PFL algorithm, the orange line, obtains better accuracy performance than other methods. And also we can find that the performance of the existing approaches like the FedMD, FedDF, and pFedDF, they are worse than the proposed method. The reason is that these methods only produce 1 global soft prediction, which cannot be well adapted to each client, because for these methods, they don't consider the personalization issue. They just consider the generalization issue. That's why the proposed methods will outperform the existing methods. And there are some other observations found in this paper. The first one is the effect of local epochs E. The author said that there still exists a trade-off between the computations and the communications by adjusting this local epochs E. The larger E requires more computation at local clients, and the smaller E needs more global communication runs. The second observation is the effect of these distillation steps R. The larger value of R cannot lead to better performance. Therefore, the authors choose this distillation step R equals to 1 in this paper. The third observation is the effect of public data sets. The author said that the different public data sets have little effect on the performance. For example, if we choose different public data set, the test accuracies are similar. So the different public data sets have a little effect or no effect on the training performance. The last one is efficiency evaluation. The authors measure the communication overhead of their proposed algorithm. They compare their proposed algorithm KTP-FL with the existing personalized federated learning approaches, where we need to transmit the model parameters. But for their proposed method, they only need to transmit the public data set and the soft prediction. They only need to transmit the data and that probability vector. Therefore, their communication overhead is much smaller than that of the conventional federated learning methods. Finally, let me conclude this paper. This paper is the first to study the personalized knowledge transfer in federated learning. And they propose a knowledge coefficient matrix to identify the contribution from one client to other clients during the local training. And their proposed KTP-FL algorithm outperforms the existing approaches in terms of the final accuracy and the communication overhead. So that's it. Thanks for your listening.
Any questions, guys?
Hey, Dian, I have a few questions.
Okay.
First of all, I wanted to know that generally, if you try to do the aggregation, then it's kind of argued that the personalization is kind of lost or it is degraded. So how does this paper preserve the personalization while still doing the aggregation?
Okay. I mean, from this loss function, this term represents the personalization, and this term somehow represents the generalization. So it can consider both the personalization and the generalization during the training. That's why they preserve the performance.
Okay. And also the C, which is your matrix, right? The knowledge coefficient matrix.
Yes.
Physically, what exactly does it have? Does it have like the predictions or the feature map, or what exactly is the content of it? How do you know that what is like? How do you store the knowledge?
Okay, so for this C, it can be seen as a weight, since it can estimate the contribution from client M to client N. Since this term is the teacher's knowledge, and this one is the knowledge from each client. So this CMN can be seen as a weight. Actually, we don't know how to calculate this weight. So in this paper, they treat this coefficient as a control variable because they optimize this C matrix. Actually, we don't know how to calculate it, but we can let the machine to learn it by some learning algorithm, by the gradient descent method.
Okay.
Yes.
And so then you will have this C is maintained only at the server, right?
Yes. Yes.
So the server is going to compute this, like running the greedy algorithm or any other procedure that it follows during every step, right? During every epoch.
Yes, every communication round, they need to calculate this C.
Will this add any kind of overhead for computations, or will it cause any kind of delay? Because this is something that's extra per round.
Yes, but they don't see the computation overhead. They only consider the communication overhead. And actually, I think for this distillation step and this update C step, I think is only one step. Since if we look at their learning settings, it contains 20 local training epochs and 1 distillation step. So I think the computation overhead will not be large. It should be very small.
Okay. I just have like one basic question over this same thing that you have 20 local training epochs and 1 distillation step, right? So is
Yes.
this like corresponding to your communication round, like the global communication round that we have in federated learning?
Yes, for each communication round, we take 20 local training epochs and 1 distillation step.
Okay, so which means that your coefficient matrix computation happens only during this 1 step.
Yes.
Okay, okay, got it.
Yes.
I had one more question. You were like saying in the beginning that most of the other related personalized federated learning papers usually have the regularization term for doing the personalization.
Yes.
Right? So I see that even this paper uses such a regularization. So how different would this work be compared to the other work?
Okay, I think the most different things is for the existing works, they don't consider the personalization of this soft prediction. They just, for example, for these teachers soft prediction, it should be the same among all clients in existing approaches. But in this paper, since we have this CMN term here, so this teacher's soft prediction will be different among clients. So I think that's the difference between their method and the existing methods. Okay. Because they consider the personalization soft prediction.
Okay. I have just like one more related question. Can you go back to the regularization term page?
Yes. Here.
Yeah, this one. So the N is your number of clients, right? The capital N in your regularization term.
Yes. N is yes.
But what's like the physical meaning of having like the difference between the coefficient matrix and like the identity matrix by N over there? Like having the L2 norm between them, like what could be the meaning of having that? Like how does it equate to showing some perspective?
Yes, I think you want to know the physical meaning of this 1 out of N, right?
Yeah, I mean, like if it was just C, I would know how personalization would act. But yes, I'm just like wondering why you have like
yes, I think the physical meaning of this regularization term is that they want to guarantee the sum of this coefficient matrix should be equals to 1. Therefore, we have this this KL divergence will have the physical meaning. For example, the sum of the CMN should be 1, and how to guarantee that? We need to have this regularization term, and we need to set this term equals to 1 out of N. We want to guarantee the sum of this weighted should be 1.
Okay, I see.
Yes.
Okay, got it. Yeah, that's all I have. Thank you.
All right, thank you.
Dian, for those equations, could you explain again the trade-off between the personalization and the generalization?
Okay. For example, if we don't have this regularization term, which means we set rho equals to 0, and in this situation, if we want to optimize this KL divergence function, we need to set CNN equals to 1, and for the other CMN, we need to set them equals to 0. So in this situation, this KL divergence loss should be 0. That's the optimal solution. And in this situation, we only have this conventional loss function term, and it only considers the personalization. So that's the personalization part. And for the generalization, if we set this rho equals to 1, which means if we have this regularization term will enforce each coefficient C approach to 1 out of n. And in this situation, the target client n will learn the knowledge from from other clients equally. So we preserve the generalization. So that this rho can trade off the personalization and the generalization.
Okay, I can understand that from the mathematical point of view for this. But just intuitively, for this kind of a teacher and student model, right? So, yes. You know, you need to, as a student, the coefficient between the teacher and student, if your things are close, then probably the coefficient should be larger. But if your things are quite different from each other, then the coefficient should be very small, right? But
yes, I think that,
yeah, go ahead.
Yes, go ahead. You go ahead.
No, just like, for example, if you are my student, because your research interest is close to my research interest, so our correlation should be kind of big, right? But if you're saying, okay, another mechanical professor and you, and your guys' research probably far away from each other, you guys' correlation should be kind of small. I mean, physically.
Yeah.
Right.
Yes.
So I think this is C matrix. I mean, intuitively should be reflect that that kind of phenomenon, that kind of you know, the ground truth, instead of be used as you know, optimization parameters or something.
Yes, I think the author they set this CMN term to represent this contribution, but the other side they don't know how to select this parameter, so they treat it as an optimization variable and use the optimization methods to solve it. Actually, we don't know the specific value of this CMN, and the other side we can optimize it by formulating this loss function and solving it with the gradient descent methods. And finally, if we approach the convergence point, and the value of the CMN will reflect the contribution. So that's their argument.
Okay, Pamela, let me ask you that question. I think you're the most familiar with the knowledge transfer things in our group, right? So what do you think?
Okay, so if you were to measure the correlation, I think the values would be like higher if they're closer, like you said. But this is a very new kind of a metric that they're using, Dr. Pan. I think, like Dian was saying, I think it's hard to use this to measure this. Instead, if we use some kind of other metric, like something that we use, if we use a feature map, and maybe at every round, if you see what is the difference between what the teacher is predicting and what the student has learned so far, maybe that we can use something like that instead, which will be easier to measure than using this one.
Yeah, Dan, by what you're saying, like, you know, if we reach the convergence, somehow the C matrix kind of automatically find a way to represent the relationship between those teacher and student, right?
Yes, and the authors, they also propose a simplified version of this coefficient matrix. They propose the similarity matrix, which means they measure the similarity, cosine similarity between these two S terms. If the similarity is higher, we set the larger value of this coefficient. If the similarity is lower, we set the smaller value of this coefficient. And the simulation results show that their proposed method outperforms this similarity-based methods.
Well, that's only related to their optimization objectives, though. But if we talk about the physical meaning, this CMN matrix should be a fixed one instead of a dynamic one. You can adjust as optimization parameters. You know what I mean?
Yes, I know that.
You just do some like a partner suggested feature comparison or something, right? So this metric should be a kind of a fix.
But actually, we don't know the performance of this fixed matrix, I think. I don't know which one is the best one. So this paper, they parameterize this matrix and optimize it.
Okay, I think I need more knowledge to digest this one.
Hi, Dan. I also have the similar question about this knowledge coefficient metric. You mentioned the Federated, right? The 15-page, I think. And you say that doesn't consider as a personalized federated learning distillation, knowledge distillation.
Yes.
But in their paper, they regard this approach as a personalized model distillation, and the personalized stage is at the end. They use they fine-tune the global model with actual epochs on the local data sets. And I see this paper also do this step, right?
Yes, I think for this personalization issue, I think it refers to this term.
Yes.
For FedMD, I think for all clients, this teacher's soft prediction is same. But in this paper, the soft prediction of all clients is different. I think that's another personalization issue. Yes.
Yes, indeed, that's the difference. So they use the same term for different meanings. I get that. So my question is, in their paper, they didn't have this knowledge coefficient metric. They only use the averaging the average local updates as the teacher, right? And so their matrix is fixed, as the Dr. Pan said. And in this paper, they regard this metric as a parameter, and they want to get this optimal metrics. So my question is, did they show the final metric?
Actually, they didn't show that. I also want to know that metric, but they didn't show that.
Yeah, so from my understanding, for each client, let's say it's client N, and if the teacher has like the weights, each client of this metric, the weight is only is 1 for the N's update, and 0 for other updates. So they will get the best KL divergence, right? So they should get the minimal loss.
Yes, but that's for the personalization. We also want to guarantee the generalization, as I mentioned.
Oh, I see. So, I see. So they use the load to control this trade-off.
Yes. Since if we have a very good performance on training data set, we cannot sure that we have the best performance on this test data set. So we need to trade off the personalization and the generalization. we also need to involve some other informations from other clients.
I see. I see.
Pavna, can I ask you another question?
Yes, Dr. Pan.
Yeah, for the general personalized flat learning paper, right? What's their formulation looks like? I think they also should consider both the personalization, utility function. At the same time, they want to probably consider the data diversity as well, right? So what is their loss function looks like?
It kind of looks very similar to this, Dr. Pan, but just that they don't have this kind of knowledge coefficient matrix.
Yes.
But they just have this.
They still have something like the KL divergence to show, the say what is we call it generalization or whatever, right? So yeah.
Yeah, if you were to consider a paper without the knowledge but just the personalized federated learning, then I don't think they use the KL divergence there. I think they use the cross entropy loss instead.
Oh, okay.
Because like they don't have like teacher and student, so they do not do this kind of measurement. But instead, they will only look at the global model versus the local model trained by the client. So they can just use the cross entropy for that.
Actually, both those metrics are used in different papers. You can choose both.
At the end, did they compare with I know you show one personalization scheme, but did you check that scheme? What the loss function looks like? Yeah.
Yes, I checked that scheme. I think for, let me show. Actually, I don't have the paper on my hand, but I checked the algorithms. For this one, I think the loss function should be similar. As I mentioned, the difference thing is for this method, they don't consider that coefficient matrix. They just aggregate all the soft predictions. And for this one, for FedDF, I think Liang has already presented this paper in our Shalom. And for this method, they only maintain one global model, which means they don't consider the personalization issue. They just maintain one global model by using this knowledge distillation. That's the contents of these two papers.
No, I want to know the personalized one. I want to know why your formulation, your objective function in this paper is better than the general personalized formulation. Like Pauna said, probably in there.
Yes, yes. I think the different thing is they set this CMN here. I think that's the most differences between their paper and the other papers, since they not just simply aggregate all the soft predictions, they use a weighted way to sum them.
But here you use KL divergence, right? So if we use a cross entropy or some other things without CMN, so it still shows certain kind of a data diversity. I just try to figure out why this formulation is better than the general personalization formulation, in kind of theoretical explanation. Simulation, definitely, you can show the advantage, but is there any kind of theoretical?
Yeah, I think the key component is personalization. For each client, we have different teachers. For example, for client one, maybe we need to learn some knowledge mainly from client 2 and client 3. And for client 4, we mainly learn the knowledge from client 9 or client 10. I think for each client, we have different teachers, but for the existing approaches, for each client, we have the same teacher. We learn the same knowledge. I think that's why their method outperforms the existing methods.
Okay. Yeah, probably I need to check those personalized fair learning paper again. Yeah.
Yes.
Yeah, but probably you can also check those papers to say if we don't use the kind of teacher-student model, we just use cross entropy or some other approach to represent the data diversity. So is there any, more detailed and maybe deeper, theoretical explanation for that? More insightful explanation for that? But let's leave that question, off the seminar. We can further check that.
Okay, sure.
Any other questions?